Hello and good evening, everyone out there. Thank you very much for joining us this evening, and welcome to our second Atom Society live streaming event. Everyone at the Atom Society would obviously like to thank you for joining us once again. And on a personal note, I'd like to thank you for all of the positive comments and feedback that you gave us from the previous talk. So, unfortunately, our chairman was going to pop on to but unfortunately he's had technical difficulties. So we will have to proceed without him, and hopefully we can get him involved in June. As I mentioned in my email, we're going to start this evening to try and reintroduce our science snippets. It's a part of the evening that we on the committee all really enjoy, and I think a lot of our members do as well. And so we're going to see if we can't try and reintroduce it. So if you do have any science snippets that you've seen over the past few months, I guess, because we haven't done it in a while, please do write them in the comment section on the YouTube video, and we can bring them up on the screen. So I can kick things off with Alphonse from our very own committee had a science snippet. So I'll just get Alphonse on the call and he can go through, he can go through the story about the scientists in Argentina finding the biggest ever megaraptor. Alphonse, tell us more.
Yeah, hi. I've just found that you all remember this raptors from Jurassic Park, the little vicious, fast dinosaurs, which were always like hunting in a pack of three. So they were only like 3-4 meters big, but now they have found one in the south of Argentina, 33 feet, so 10 meters high. Okay, they haven't fully dug it out yet, but like they can extrapolate it from the bones they found. So it's almost as long as T-Rex, and it just appeared on the Earth just before the dinosaurs disappeared, were all wiped out. So it's kind of the last meat-eating dinosaur. And if you get my screen in, I even have a picture of this. So yeah, this is the one. And let me see. You can see it's famous for its long claws. So that's almost like a dagger or a sword. It's a good part of a meter long. And I think I also have a few pictures here where you can actually see the paleontologists trying to dig them out. I wouldn't see that they are bones, but apparently they are. So yeah, here you go.
Okay. Very cool. Thank you very much, Alphonse. So we haven't got any more science snippets come through yet. I do have a couple of my own. So an update on I'm sure you've all heard that there is a COVID-19 vaccine trial going on for a vaccine that was developed at the University of Oxford. And while we won't hear results from the human trials for at least a few weeks, probably longer, they have published in the last week on bioRxiv some of the preclinical data. So that's when they were testing the vaccine in monkeys, and it's very promising. So the vaccine was shown, the animals that were given a single dose of the vaccine, some of them had antibodies within 14 days. And all of the animals who were given a higher dose showed antibodies within 28 days. The virus was unable to inflict damage on the lungs in those that had been vaccinated, and it wasn't able to replicate in the lungs. So that's very promising. Obviously, we'll have to wait and see for the human trials, but that sounds pretty good. And looks like we have another science snippet from Andy Duxbury. So he says astronomers have found the closest black hole yet at just 1,000 light years from Earth, which is close enough to see the stars that orbit it without a telescope. So that's pretty cool. And I don't know if you could maybe post a link to the news article that you saw that in, or let us know where you found the information in case people want to look into that more. That's pretty exciting. The only other news story that I had was a little bit more lighthearted. Researchers at the University of Newcastle have found that dogs also have a teenage period, just like humans. So obviously we all know the stereotype of the teenager. It's very disobedient and disrespectful. And it turns out that dogs go through a similar stage, usually roughly around 8 months old, where they become less responsive to commands, more disobedient, more unruly. They're trying to push the boundaries between them and their owners. Unfortunately, this corresponds with the age when a lot of dogs get given up for adoption because the owners think, oh God, I can't control my dog. I can't be a dog owner. They're just a teenager. Just give them a few months, they'll calm down. It's fine. All right. Okay. We don't appear to have any more science snippets. So I guess we can move on with the main event, so to speak. And so I will hand back over to Alphonse, who will introduce our speaker for this evening.
Yes, so it's a pleasure for me to introduce Josh Dorrington to you. He received his MPhys, so he's a physicist from the University of Exeter in 2017, and then came to Oxford to do his PhD in environmental research. And what he is working on is, I have to read, large-scale, slowly evolving structures or anomalies in the North Atlantic. And I wouldn't know why that's important, but apparently that is actually what governs, or everybody knows, the weather is always coming from the Atlantic. So those things are the ones that influence our weather here. And the things he's looking for was like how they influence the extreme weather. And if you understand those, you can make the weather predictions, of course, more accurate. That's, however, not what we will talk about today. Today, he will talk about supercomputers and seagulls and the story of weather predictions. Yes, let us welcome Josh.
Hi, everyone. Hi, Alphonse. Thanks for that. So thanks for having me. As Alphonse said, I'm Josh Dorrington. I'm from the University of Oxford, where I'm in the Atmospheric, Oceanic and Planetary Physics department. And today I'm going to be talking about supercomputers and seagulls, the story of weather prediction. I'm going to try and cover a few topics in this talk. The first one is, what is a weather forecast? How is a weather forecast made? What goes into that process? Then I'm going to talk about where weather forecasts come from. How do we get to the current state of the art in weather prediction? And then I'm going to talk about what makes this problem of weather prediction so uniquely challenging, why we're still struggling to make good forecasts even in the 21st century. I'm going to talk briefly about climate modeling and how that's similar and different to weather forecasting. And then finally, I'm going to finish by talking about the state of the art and the cutting edge in weather prediction at the moment and what you can hope to see in your weather forecast in the next 10 years or so. So let's start at the beginning. Say you want to make a weather forecast for the next week or two. How do you do that? Say you want to start your forecast at midnight tonight. The first thing you need to do is to gather observations, measurements all around the Earth's surface. And normally you'll collect 6 hours of measurements. So from 9 p.m. to 3 a.m., you'll collect all the measurements all around the world of what's happening. And this is a vast process. You have weather satellites, and there's probably about a dozen weather satellites in orbit, taking pictures of the Earth's surface, looking at where the clouds are, measuring atmospheric humidity, temperature at the upper and middle atmosphere. People have sensors attached to aeroplanes, which are taking measurements of opportunity as they fly to and fro across the globe. We have ground-based sensors. This big white golf ball bubble in the bottom here is a weather radar, and that takes radar images of clouds from the ground surface and maps out the sort of low-lying clouds. We also, of course, have a long history of ground station measurements. In the bottom right here, you can see a picture of the Green Templeton Observatory in Oxford, and this is actually the site of the longest continuous temperature record in the world. Starting in the 1830s, there's been a daily measure of the temperature and wind speed there. We also send up probes flying on big helium balloons up into the atmosphere, and they can broadcast the winds and the pressure as they go. And increasingly, in the modern age, we need to know what the ocean's doing. And so we have this vast network of yellow buoys that can sink up and down into the deep ocean and up again, and they can tell you the temperatures, the currents, and the salinity. So this is a huge endeavor, and you collect all these measurements, and then to collect them in takes about an hour. So you stop measuring at 3 a.m., and by 4 a.m., you have gathered all your measurements all around the globe. But at this point, you have a whole lot of spotty little measurements here and there. Maybe they disagree with each other. They're not tidy. They're not nicely organized onto a neat grid. It's going to be very difficult to do anything with those. And so the next thing you have to do is called data assimilation. And that's basically the process of taking these sparse jigsaw pieces and joining up into a continual whole. So this little diagram at the top here shows your yellow scattered dots for your observations. You don't have observations everywhere, but the weather model has to know what's happening everywhere to initialize it. So how do we fill in those pieces? Well, what you have to do is you have to take your old weather model. So we have a weather forecast we used yesterday, and of course it's not going to be as good as today's because we didn't know as much then as we do now, but it's valid everywhere on the Earth's surface, all the way from the ground up into the top of the atmosphere. And so we can use that as an initial guess of what the weather is going to be doing today. And everywhere that old forecast disagrees with our new observations, we nudge it towards our new observations so that we can produce this orange line here, and you can see it passes through all our observations, but it's got no gaps and no disjoints in it. So this process is very complex, and it takes about an hour. And so now you're up to 5 a.m. and you've got a nice gridded set of data that you can use to start making a weather forecast. And now you begin the meat of the matter, which is to run your weather forecast model. So nowadays, most weather forecasting centers will run a 2-week forecast, 10 to 15 days into the future, and they'll run that twice a day. And it's expected that you can get that model to run in an hour. So you have to make a 15-day forecast in an hour by 6 a.m. And this is no mean feat because the amount of complexity in a modern weather forecast is vast. We have to divide up the globe into little boxes, and a modern weather forecast has perhaps 1,000 boxes, both north to south and west to east, as well as 100 vertical layers through the atmosphere, taking you all the way from the very near surface of the ground to the very top of the stratosphere, high above where the highest jets are flying. And in each of those grid boxes, we're trying to calculate the movements of temperature, humidity, pressure, the winds, radiation coming from the sun. We're also trying to represent all sorts of processes which are smaller than our grid boxes, but which are nevertheless very important to shaping the weather. This is things like winds blowing over mountain ranges. Mountain ranges have a dragging effect on weather. They slow it down, and we have to represent that. We have deep convective clouds in the tropics, which pump energy and moisture up and down to the atmosphere. We have to try and model those. You have to think about what the ocean's doing. The ocean can be a source of heat, or it can absorb heat, depending on its relative temperature to the air, and that's really important for shaping weather. And we also have to think about aerosols. These are pollutants that are produced both naturally and by anthropogenic sources, which are really important for affecting cloud formation. And we have to try and model those and measure those. So this is a really complicated process, tracking actually 1 billion different numbers at every time step of the model. But we do it in an hour. And at that point, you can start something called post-processing. What is post-processing? Well, it's basically just adding value to your forecast. So doing all sorts of things that make it more valuable. The simplest of those is correcting any systematic errors that you know your model has. So, for example, some models are always a bit too warm, and you know that's the case, so you subtract that bias away, so you're not making a misleading forecast. You might do something called downscaling, where you might know, for example, if you live in a mountainous community, you might know that weather forecasts aren't as good there because the small valleys and mountain peaks that guide the winds and rain aren't properly represented in the model. They're too small. But again, we know this, and so we can use past observations and statistical relationships to produce smaller scale forecasts from that large overall weather forecast. We also add all sorts of important details that people really care about, but that the model doesn't know about directly. That's things like predicting hailstone size, the distribution of lightning strikes, the chance of a tornado spinning up, or the risk of flash flooding. We also might want to do some blending of different forecasts. There are many different weather centers, all of which produce their own forecasts, and sometimes people find clever ways to mix those together to create a sort of super forecast that is better than any of the others individually. Finally, there's a process called nowcasting. This basically means at this point in the day we're at 6:30 a.m. 6 hours have passed since we decided to start making our forecast, and things might have changed a bit since then. In fact, we have more up-to-date measurements of where the clouds are, and so sometimes we will want to override the early part of our forecast with the output of our radars or more recent observations, where we can correct it if we know it's already gone a bit wrong. So this takes about another half hour, and then we get to the really important part, which is disseminating the forecast, making sure that people know what's being predicted. So for many of us, our engagement with a weather forecast will be on the news. A TV newsread weather person will tell us what's going on with the big map, and there'll be the temperature marked in a few key locations, or you might have your weather app on your phone. But that's only a small part of how people find out about the weather. There's also things like the shipping forecast, which is apparently a lot of people are very keen on, and not just sailors, but sometimes people like to listen to it. Apparently it's quite soothing. And also, there are consultant meteorologists who will go out and talk to businesses or government or NGOs and give them a customized, bespoke weather forecast. So, for example, if you were Airbus, you might really want to know what the wind speeds were going to be over Heathrow Airport. And so you might employ a consultant meteorologist who would bring you first thing in the morning a detailed analysis of the winds in that area that would affect your business. And that kind of brings us on to the final and the most important part of the weather forecast timeline, which is application. What is, how do people actually use the forecast? So in the top left here, you'll see a family enjoying a picnic on a sunny day. And for many of us, that's how we think about the weather forecast. It helps us guide our everyday decisions. Do I pick up an umbrella? Do I need a raincoat, or can I wear shorts today? But that's really not what most of the value of a weather forecast is. It's some things like the agriculture sector. People want to know when they can plant or harvest their crops. If you leave your crops out too long and they get caught in a heavy downpour, you might ruin your harvest. Similarly, if you're in the energy sector, increasingly nowadays, with the rise of wind power and solar power, the energy production can be very dependent on what the weather is doing. And if you were responsible for supplying energy to many people's homes, you might want to know if it wasn't going to be very sunny or very windy, you might have a shortfall, or you might have to buy extra power to make sure you can supply your customers and to avoid blackouts. Also, logistics and transport really depend on weather. I'm sure that the driver of this van here, or this lorry, sorry, had wished that he'd checked what the wind gusts were going to be before he drove over the Severn Bridge and got tipped over. Similarly, the captain of this shipping container cargo ship would have liked to know that there were going to be strong waves that were going to knock some of his cargo into the ocean. And of course, aeroplanes can't take off or land in high winds, and that can be very important to know in advance. A recent development, which is really valuable, is that humanitarian organizations are now starting to use forecasts. This picture in the bottom left it shows the Peruvian Red Cross handing out supplies and resources to people who are at a high risk of flash flooding. But the important thing here is that they're handing out these resources in advance of the event, based on a forecast of likely floods. And that means that people can take preventative measures instead of just having to help people after they've already lost homes or loved ones. So this is a vast process. I mean, the annual running costs of a weather forecast centre can be measured in tens to hundreds of millions of pounds a year. It takes thousands of dedicated meteorologists, computer programmers, consultants and software engineers. The observations are very expensive. A network of weather satellites is worth well over £1 billion. And the models need to be able to calculate 1 billion variables that we have to track everywhere on Earth. And that needs vast supercomputers that fill whole warehouses that are capable of performing 1,000 trillion calculations every single second and that store millions of gigabytes of data in a year. The economic value of this vast pipeline to the UK alone is estimated to be £1 or £2 billion a year, and it's estimated that hundreds of lives are saved through things like avoided shipwreck. So how did we get here? Well, I think now there's supposed to be a short break, and I'll tell you the rest after that.
Thank you, Josh. We will be back at 8:05. So we'll see you then.
Hi. So before the break, I explained how a modern weather forecast works, how it, what it involves, and explain how much detail there is that goes into it. But how did we get to this point? I mean, what was how did this process begin? Well, much like a forecast, it all started with observations. In the early 19th century, people first started to map out in a systematic way what was going on in the sky. It's hard to imagine now, really, but for the longest time, the sky was a strange and distant land. People didn't really know what was up there. People debated whether it went on forever or whether it had a hard top at the top of it. And it wasn't until the 19th century that people started to do things like fly weather kites. They started to collect wind measurements in different places and then try and piece them together into consistent weather charts. People like William Ferrell in the top right here started to understand that the Earth has huge circulations of air moving up and down, and that these are what give us the trade winds that blow east from America to Europe and west again back from Africa to America. People started to create more sophisticated instruments like the pocket barometer, which could be taken up to high places to measure changes in pressure. And the aeronauts, balloon explorers of that age, started to gain enough confidence in their methods that they could start taking up passengers, including intrepid scientists such as William Glazier, who made a now famous flight across England in a hot air balloon and produced a beautifully illuminated book of his findings. You can see this in the bottom right here, this graph from his book that shows his journey up and down through the clouds. This was an age of discovery, and people were learning a lot about the atmosphere, but it was very much a mapping exercise, trying to understand what was happening. There was no idea that the weather could be predicted. And in fact, when one MP stood up in Parliament in the 1850s and said that soon perhaps advances in modern science would allow us to forecast the weather a day or two ahead, he was actually laughed out of the chamber. It was considered so ridiculous. So what changed? What made us move to predicting the weather? Well, perhaps the main catalyst event was something called the Royal Charter Storm in 1859. This was a monster of a storm. 100-mile-an-hour winds span up in the Channel over France. They swept up across Devon and Cornwall, devastating the coasts there, up past the coast of Anglesey to the west of Wales, before finishing up along the top of Scotland. 800 lives were lost, 133 ships sank, 90 more badly damaged. This is more sailors lost to shipwreck than in the whole of the previous year, and its name came from the sink of the Royal Charter, this ship here that washed up on the coast of Anglesey. All hands lost, drowned. And there was no way of predicting it. No one knew that this storm was coming, and so no one was taking any action to avoid it. This sort of disgusted one man in particular, a man named Admiral Fitzroy. Fitzroy was responsible at the time for the Meteorological Office of Trade, and his job was to map out more precisely the trade winds so that ships could make faster and more efficient journeys to and from the Americas. But he dreamed bigger than this. He thought that with his network of observation stations, he could produce storm warnings so that incidents like the Royal Charter storm would never happen again. And he was aided in this quest by a modern invention, the electric telegraph, with which messages could be sent that far outstripped the swiftest tempest in celerity, as one newspaper put it at the time. His idea was that he would station that when one station, perhaps in the east of England, observed a storm coming, signals could be rapidly sent up to other harbours across the country. A drum could be beaten and the harbour closed. No more ships allowed out. And basically, this worked. The number of deaths from shipwreck went down dramatically. And this is what we would now call a form of nowcasting, using your latest observations and quickly disseminating them as fast as possible so people can act on them. But Fitzroy dreamt bigger than this. He thought he could produce a true forecast of 1 or 2 days ahead. And he published these forecasts in the newspaper at the time. And this struck the public imagination. They were wildly popular. For a long time, newspapers had included weather forecasts, much in the same way that a modern newspaper contains horoscopes. They were viewed as a bit of whimsy, a bit of fun, but they didn't have any sort of true reliability to them. But now, here was a forecast with the official backing of the state, saying it used the latest scientific measures, and people were relying on it for things like going to the Derby Day, would take or leave behind their umbrella on the basis of Fitzroy's forecasts. It's not actually clear how good these forecasts were, and they were very vague. Britain was split into 4 sectors, north, south, east, and west, and the forecast would say things like fair, chance of rain, which isn't a lot of detail. And the method he used to make these forecasts, which we would now call a method of analogues, wasn't very reliable. And that basically involved looking at his weather chart of what was happening across England, and then looking at old forecasts or old days and finding a day that looked similar to today, and then taking the next day after that as his forecast. Basically saying that, if the weather was similar today, then it should be similar tomorrow. And this doesn't really work. And we can kind of see this by looking at the literature of the time, what people thought about state-of-the-art weather forecasting at the end of the 19th century. This is a quote from Thomas Hardy's Mayor of Casterbridge, in which the protagonist, Henchard, wants to know, he's in the agricultural sector, and he wants to know the forecast. What is the harvest fortnight to be? And the weather forecaster says, by the sun, moon, and stars, by the clouds, the winds, the trees and grass, the candle flame and swallows, the smell of the herbs, likewise by the cat's eyes, the ravens, the leeches, the spiders, and the dung mixen, the last fortnight in August will be rain and tempest. So, this is what people were using at the time. It's not exactly a rigorous, empirically based scientific approach to weather forecasting. So how did we move beyond? How did we move from measuring the atmosphere to truly understanding its motions? Well, for this, we had to wait until the 1910s and the important work of father and son team Wilhelm and Jakob Bjerknes, who came up with the Norwegian cyclone model. And the key here was they realized how important the movement of air was. It turns out that if it's cold today and warm tomorrow, it probably isn't that the cold air has heated up, but that the cold air has been displaced by warmer air rushing in from the south. When Jakob had this realization, he was fighting on the front lines in World War I, and he coined the evocative phrase of weather fronts, cold air and warm air clashing in battle, and where they met, producing large storm clouds. This is basically an accurate understanding of how weather works, especially in the mid-latitudes around Europe and North America. And you will still see weather fronts drawn onto your TV weather forecast, for example. But perhaps more importantly, they discovered equations which could, in theory, be solved that would take the current state of the atmosphere and tell you what was going to happen next. And it didn't take long for someone to have a go at this. Fry Richardson, he was a Quaker and a pacifist, so he was an ambulance driver in France during the First World War. And he decided to try and calculate a one-day weather forecast by hand with pen and paper. And it took him 2 years to make his 24-hour forecast in between breaks when he wasn't driving. And he published this in a book. Unfortunately, his forecast was a complete disaster. It was wildly inaccurate. And this was due to it being dominated by wild, unstable gravity waves. If you look at this picture in the bottom right here, you can see these striped banks of cloud with the gaps in. You'll probably have seen these before. And basically what it is showing is that when air goes over a ridge or mountains or a landmass, the air rises up and then crashes back down again on the other side. And this oscillation up and down produces these gravity waves. And because Richardson didn't have enough observations, his measurements were too scattered, and he certainly didn't have any sort of modern data assimilation, he didn't really know what was happening in the gaps between his measurements, and so his results were physically inconsistent and produced these wild waves. That this would happen was actually predicted by a mathematician called Max Margules a few years earlier, and he had concluded from it that weather forecasting was immoral and damaging to the character of a meteorologist. But Richardson thought otherwise, and he dreamed a bit bigger. He said that perhaps someday in the dim future, it will be possible to advance computations faster than the weather advances, and at a cost less than the saving to mankind due to the information gained. But that is a dream. He had a vision of a weather forecast factory where tens of thousands of human computers would sit around and they would each calculate the weather at their particular spot on Earth. When they were done, they would pass their results to their neighbor under the guidance of a comptroller in a tall tower who would shine a torch saying, now we're calculating the weather at this spot on Earth, pass on your measurements. Such a factory, of course, never arrived, and Richardson's ideas were too far ahead of his time. He really had no chance of success for a few reasons. One, at the time, there weren't enough observations of the 3D structure of the atmosphere. It's actually really important to know what's happening high up in the atmosphere to produce a good forecast. And even when people were flying kites high up, it was very slow to recover the measurements. They would have to be found where they landed, gathered, and sent off. There also wasn't enough understanding of the algorithms needed. How do you turn an equation into something a computer can solve numerically and stay stable? He also didn't have enough people. Richardson had estimated he would need 64,000 human computers to make one of his factories, but more modern estimates say he would have needed more like 1 million people, which is even less realistic. So for the long time, this sort of method of analogs that Fitzroy pioneered was the state of the art in weather forecasting, now using these ideas of weather fronts as brought in by the Bjerkneses. But this started to change during the Second World War. In the Second World War, there was a vast increase in demand for trained weather forecasters. And this increased the numbers by a factor of 15, from hundreds to thousands. And what's more, they were trained up by a man named Carl Gustav Rosby, who was from this physical, mathematically rigorous school of Norwegian meteorology. And most of these new meteorologists were recruited from maths and physics programs, and so this new mindset of physically based prediction was well on its way. Also, the observations were getting much better. The fighter jets and the invention of the radio probe that could send back its measurements without having to be collected meant that we had much better measurements of the 3D structure of the atmosphere now. But there was one invention that was developed for the purposes of code breaking, which led to the greatest change of all. And that, of course, is the development of the mechanical computer. The first weather forecast made on a mechanical computer was on a machine called ENIAC, the electronic numerical integrator and computer. And this was built actually for the purposes of calculating ballistic trajectories of missiles, but it was completed too late to be used in the war and was instead repurposed by mathematician John von Neumann and meteorologist Jules Charney to produce a weather forecast. They saw this as a perfect opportunity to show that the equations could indeed be solved, except now instead of Richardson's dream of tens of thousands of people, it was tens of thousands of vacuum tubes and copper wires. They produced a 24-hour weather forecast in 24 hours. They only just beat the weather, and they only did it over a small region over America, and it wasn't incredibly accurate, but it captured the main movement of the weather, and they showed that it could be done. Instrumental to this effort were the computer programmers, primarily female, who were recruited to operate and code the machine. This at the time was seen as basically secretarial work that was not interesting enough to be done by predominantly male scientists, and often the important work that these women did has been neglected in history, but it really couldn't have been done without them. Nowadays, you can run the ENIAC computer model. It's been put onto a different software, and you can run it on your phone. It's called Phoniac. And if you want to make a state-of-the-art forecast from the 1950s on your phone now, it takes less than a second to run. So if you're not happy with your weather app, perhaps you can have your own go. So throughout the 50s, computers were getting faster, they were getting smaller, they were getting cheaper, and a lot of this effort was being thrown to weather prediction. And people were starting to speculate that perhaps soon we would solve the weather completely, that we would be able to identify the pattern that guided which storms followed which periods of good weather and so on. And we would be able to produce forecasts for years ahead in the same way that we can predict the motions of planets centuries ahead. But a spanner was thrown in the works by the discovery in the early 1960s of chaos in atmospheric systems. So Ed Lorenz was working with Margaret Hamilton and Ellen Fetter on, they were playing with the new toy of the time, the desktop computer, a computer so small you could fit it on a single desk. And they were playing with simple models of the atmosphere, feeding in code on little punch tape. And they noticed something rather strange. Sometimes they would run their model, and then they would want to pause it and start again later. And to do so, they would record the numbers the computer was putting out and save them for later, and then put them back in again. But when they wrote those numbers down, they were only using a couple of decimal places to save time and paper. But in the machine, it used 6 decimal places. And when they went to recalculate results later, they found something rather strange, that the results would stay similar for some time, but then they would rapidly diverge and they would lose all similarity to each other. And once they realized this wasn't a bug, but was in fact an important part of how the atmosphere works, Lorenz sort of coined the realization that the neglected flap of a seagull's wings in Brazil might start a chain of events triggering a tornado in Texas. This is the idea that a tiny shift in the initial conditions of the atmosphere could grow and grow over time and produce a completely different weather system. Over time, the seagull has morphed into a butterfly, perhaps that's considered more aesthetically pleasing, and is now known as the butterfly effect, but originally it was a seagull. So how does it, why does this happen? How does this work? Well, like many systems in the real world, the atmosphere is very complicated. It has many effects happening on many different size and time scales, and all those effects interact with each other. So a tiny change in the updraft created by a seagull's wings might affect how a cloud forms. A move in the position of that cloud might alter the development of a cloud bank. The presence or absence of a cloud bank might affect the development of a large-scale storm or cyclone system, and that cyclone system might affect the development of the large-scale planetary waves, which are the largest structures we see in the atmosphere. Of course, this doesn't happen instantly, and towards the end of the 60s, Lorentz sort of produced calculations to suggest that it should take about 2.5 weeks for even the smallest perturbation you can imagine to grow so large that it would ruin the planetary scale weather forecast. And so he set a sort of predictability horizon that we would never be able to forecast beyond 2.5 weeks. So what did forecasters think of this pronouncement at the time? Well, basically nothing. They basically ignored it for a few reasons. One is they weren't operating on timescales of 2.5 weeks. They were still trying to produce a good weather forecast for 3 or 5 days. Secondly, there was an incredible optimism in weather forecasting, what's now called the quiet revolution, which relied on 2 factors. One was Moore's law had kicked in. Every 18 months, the size of transistors would halve, and so computers got twice as fast and twice as small. And this meant more and more complicated models of the atmosphere could be used. Additionally, observations were getting much better, and this really hit its zenith in 1979 with the global weather experiment. This was a massive global cooperative effort to try and take really good observations all around the Earth's surface for a whole year. It involved the launching of 5 weather satellites, hundreds of weather balloons, flying dozens of aircraft through storms, and setting ships across the ocean, placing weather buoys. And they took a degree of comprehensive measurements that then wasn't equaled again for perhaps another 15 or 20 years. The idea was to show that if we had these networks in place, we would be able to produce really high quality weather forecasts. About this time, the complexity and detail of our observations and models was getting to the point where people could start to tackle other problems in the atmosphere, including the curious topic of climate change. In the early 20th century, theorists such as Svante Arrhenius and Guy Callendar had done calculations on pen and paper using simple assumptions about the atmosphere to suggest that if we kept pumping CO2 into the atmosphere, we would eventually warm the planet. And they estimated that this warming would be about 2.5 or 3 degrees if you doubled CO2. And that's pretty much bang in the middle of our modern day estimates using very advanced models. So they did a pretty good job. But in the 60s, sort of headed by Sikuro Manabe, people started to make computational models of climate change. These started with very simple models, just tracking the movement of energy through sunlight and clouds and how that would affect the ways that clouds distributed water vapor, sort of very loose arguments. But then eventually it led to the first true global climate model with accurate continents and with a dynamically evolving ocean. Not only the atmosphere was changing in the model, but it was also connected to an evolving ocean. And this kick-started a process which is continuing to this day. By now, climate models are far more advanced than they were in the 70s, both in terms of resolution. The grid boxes have got much smaller. From some of the earliest climate models in the 70s, you wouldn't even be able to see Great Britain. But by the mid-2000s, you can start to pick out individual parts of the Alps. But also, in terms of processes we're representing, a climate model is like a weather model on steroids. It has so many complicated processes to include. These are things like atmospheric chemistry. How is the ozone changing in the atmosphere? We have to think about vegetation. Rainforests, for example, will produce humidity in the evening, and that has effects on cloud formation. We have to think about the pollutants that we emit, both naturally and from industry, things like aerosols and sulfates, which change the way that cloud droplets form. We have to think about the sea ice, as that melts and advances and changes the absorptive properties of the ocean. So this is a huge and complicated process that requires a lot of supercomputer time to make these climate projections. And some people ask questions like, well, if chaos, as you just said, makes weather unpredictable in 14 days' time, how can we hope to model the climate? That's 100 years away. That should be completely impossible. Well, is there anything to that argument? No, is the answer. And you can understand why not with the use of a simple analogy based on this thing here. You might have seen one of these before. It's a sort of toy called a Galton board. And basically the point of it is you put your marble into the little funnel at the top, and it bounces around on these pegs, bing, 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 and then it will land in one of a number of bins at the bottom. So the question of weather prediction is a lot like putting your marble into this Galton board and trying to work out exactly how it's going to bounce off every peg and work out which bin it falls into. You might have some luck if your marble is already near the bottom when you start. It's only got a few pegs to bounce off. You might be able to predict that. But if you're putting it in at the very top, very far in advance, you're probably not going to be able to track it. It's just so chaotic. But if you look at the way that dozens of marbles fall into the board, you notice there's a pattern. You notice that statistically speaking, it's far more likely that the marbles will fall in the middle than on the edges. And so that's very predictable. You can very easily understand the statistical properties of the way that marbles fall in this system. And if we're doubling the amount of CO2 in the atmosphere, that's a bit like tilting your Galton board and then saying, well, what's going to happen statistically now to marbles that we push into our system? And of course, they'll no longer fall in the middle. They'll all be shifted towards one end, much like we know that, although I can't tell you what the weather will be in 2084 in the summer, I can be pretty sure it will be warmer than summers are now. So what's been happening since then in terms of weather prediction? What's happened since the 70s? Well, the quiet revolution of weather forecasting has continued. This plot shows how good weather forecasts are with time at different numbers of days ahead. And basically the rule of thumb is that every 10 years, weather forecasts get one day better. You can look one day further into the future with the same level of accuracy as you could. So now a forecast, a 7-day forecast in 2020 is as good as the 3-day forecast was back in 1980. And this is because the computers have got faster, observations have got better, and our understanding of the physics is much improved. But now we're starting to really push up against that 10, 15, 18-day boundary where Lorentz said you would not be able to predict beyond that point. So what do we do now? Are we finished? Is this the end of weather forecasting? Well, no, because we can use some of those useful ideas about predicting distributions from climate prediction to make what we're calling sort of seasonal forecasts. This is everything from a month ahead to a year or 10 years ahead for decadal forecasting. And this basically involves looking at what's happening now and trying to work out a distribution, a probability that different types of weather are going to occur. So we know our observations are scattered across the planet, and we know that we've had to fit them with a model to fill in the gaps. So we shouldn't treat them as wholly unchangeable measurements. So why don't we adjust our measurements a whole bunch to represent our uncertainty in our observations, and then make a whole bunch of weather forecasts? Why don't we make 50 weather forecasts and see what's going to happen then? And you might see something like this diagram here. This might be a forecast of temperature. And you might see that there's a pretty good chance it's going to be moderate, but there's a small chance it'll be very hot and a smaller chance it'll be very cold. And from that, we can make a probabilistic forecast of the weather. So maybe this would be clearer if we used an example. Some of you might know about the infamous 1987 storm, the Great Storm. This is what turned Sevenoaks in London into Three Oaks. And it was a forecast bust. It wasn't expected. A woman rang the BBC and said she had heard there was a hurricane on the way. Well, if you're watching, don't worry, there isn't. Those were the words of TV weatherman Michael Fish, and he earned him some derision because the forecast on the right here, this pale purple blob, suggests nothing bad's going to really happen. But the reality of what happens, this dark blue smudge, indicates a very strong storm and very fast winds. So is this just chaos? Was there no way to predict the storm? Well, people have asked, what if we had used probabilistic forecasting back in the 80s? What would have happened with the Great Storm? And they ran 50 different weather forecasts, all with slightly different initial conditions. And here you can see these 50 possible worlds that the forecast envisioned. And you can see that in about 13 or 14 of them, there's these dark purple smudges, all slightly different shapes and slightly different places. But the point is that there was a good chance, a 30 or 40% chance, that a very strong storm was going to occur. And if people had known that, they probably would have taken preventative action at the time. So that kind of brings us up to the very cutting edge of weather prediction. What lies in the future? Well, I've said already, we're trying to do seasonal forecasting. This is trying to answer questions like, will the next winter be cold and harsh, or will it be wet and warm? We're also trying to integrate our weather and climate models together. These were developed independently, but ultimately a weather model and a climate model are trying to explain the same system, the same atmosphere and ocean. And one of the big problems in climate modeling is lack of validation. You fit your model to the 20th century, and you're trying to predict the 21st. And how do you know that your model is any good? Well, one suggestion is that if you can use your climate model to try and predict the weather, if it's good at predicting the weather, then it should be a good climate model as well. You can sort of make that connection. So there's the idea that we're trying to produce seamless systems that can be weather models, seasonal models, or climate models, depending on how you run them. We're also really trying to get our grid boxes much, much smaller so we can resolve more and more processes. The really important one is clouds. Big, deep cumulus clouds, like in the tropics, can be only 800 meters wide, and yet they're really important for changing the energy balance of the atmosphere. So to see those properly, we need sort of 1 kilometer squares in our models. This has suggested the idea of a cloud Turing test. So there's 4 Earths here. One of them is a satellite image of Earth. The other 3 are output from super high resolution experimental weather models. And the idea is if you can't tell which ones are observations and which ones are the models, then we're doing a pretty good job. So perhaps people can post and try and work out which they think is the real world there. So that's just a few things that are going on at the moment in state-of-the-art weather prediction. And with that, thank you. And any questions, please?
Thanks, Josh. That was really interesting. And I'm sure there will be questions. Apologies to anyone who was struggling with the sound for the first part of the talk. Hopefully it was a bit better after Josh being close to the microphone. We are amateurs and this is a learning process. We don't have professional recording equipment, unfortunately. So are there any questions? So there are none at the moment, so I'll kick it off. You mentioned, obviously, you discussed the complexity of the fact that climate change prediction or climate prediction is so much more complex even than weather prediction. And obviously, we're looking at larger timescales, so perhaps the chaos effect is compounded. We've also seen reports that because of lockdown and quarantine situations all over the world, There have been drops in CO2 levels, and there have been changes to, for example, Venice or fish in the waters for the first time in decades. Do you think that a sustained period, this could go on for, a year or so, of these kinds of changes could have a significant impact, or do you think it'll end up being a blip?
So in terms of there's two things going on, right? So one is changes in the amount of aerosols, the pollutants that we're pumping out, and those have dropped really significantly. But in terms of the CO2 drop, there has been a big drop in CO2. But someone pointed out to me today, it's the same drop we need to make every year for the next 20 years to meet our Paris commitments. And also, the current CO2 emissions globally are the same as they were in 2006. So it's not like we've gone back to sort of great pre-industrial idyll. So it could give us an opportunity to launch some real system change and sort of take this as a jumping off point to emit less, but it's certainly not guaranteed that this will have a strong impact.
Yeah, okay. Well, fingers crossed more working from home, eh?
Yeah.
Thank you very much. So we do have some questions that have come in, and we have had some comments saying that it sounds much better in the second half, so that's great. So we have a question from Neil Cuthbert, who asks, is the change... Oh, it's the same question I just asked. Apologies. So hopefully that's answered your question, Neil. We then have a question from Alphonse, who says, how long does it actually take for the seagull from Brazil to be felt here?
So obviously it's not an experiment you can do, right? Because it involves a counterfactual. What if the seagull hadn't been there or otherwise? But we do think that that it's about 2 weeks to get to a sort of global scale of it takes about 2 weeks to propagate up that high.
Okay, wow, that's faster than I thought. Okay, so we have a question from Andy, who says, is it easy to tease out from the climate change models which are contributing most to the increasing global temperatures?
Sorry, which what are contributing most to?
I guess which factors are contributing most in the climate change models? I'm not sure. Andy, could you clarify on that question, and we'll maybe come back to it, and we'll hopefully be able to answer it a bit better. Alphonse asks, for how many days will we be able to make deterministic weather predictions?
So it depends what you want to predict. So if it's say rain or wind speed, not very far, and if you wanted it like an hourly resolution, then maybe only 2 or 3, 4 days. But if you want to know things like temperature, and you're happy to have maybe an average over 100 kilometers or so, you can probably do a week and a half. It changes in different parts of the world, and Europe is particularly unpredictable, unfortunately.
Yeah, okay, cool. So Andy has clarified that he did mean which factors within the climate change models contribute most to the increase in global temperatures.
Well, so it's mostly the fact that when you've got the increase in CO2 or methane or any of the greenhouse gases, that means that the atmosphere essentially becomes more opaque to radiation. So the shortwave radiation from the sun gets to the surface, no problem. But now you've put a big fuzzy blanket of CO2 around the atmosphere, that heat can't go back out to space, and so it gets trapped and warms the Earth. The thing that makes all the climate models kind of disagree with each other is primarily the clouds. So there's a lot of questions about clouds can either reflect sunlight back into space, cooling the Earth if they're quite high up and made of ice, or they can warm the Earth if they're lower down and trap heat in. And trying to understand, are there going to be more high clouds, more low clouds? Are they going to cancel each other out? This is like a really subtle question, and the errors on that are quite large. So that's why there's differences between, say, 2 degrees of warming, 5 degrees of warming. That's kind of down to cloud physics.
Okay, thank you very much. So we have a question from Bob Anderson, who asks, the accuracy of the weather forecasts does seem to be poorer since so many flights have been grounded by COVID-19. Could the measurements that these aircraft report be that important presumably to the contribution of the weather prediction?
Yeah. So this is an interesting question, actually, that we've talked about a bit. I haven't seen if it's actually if it has sort of quantitatively affect the accuracy of the forecast, but there has been, I think it was about a 40% decrease in aeroplane observations, which certainly does reduce our accuracy of our forecasts. I'm not sure how significant it really is. It might be. I know that 98% of all the data that goes into the data assimilation process comes from satellites. So that almost all of it is from these big pictures of Earth. But sometimes it's really crucial if you want to know how deep a storm's going to be, how strong it's going to be. Having something closer to it is quite important. So it could be making an impact.
Okay. I guess it'd be interesting to see how that develops the longer the flights are delayed. Cool. So we have a question from Jane Beale, who asks, do wind turbines take wind energy out of the atmosphere? And is this likely to have an effect, seeing that flapping seagulls' wings have an effect?
So, I mean, obviously you do take energy out of the winds a bit when you've got a wind turbine to harvest that, but it's very insignificant because the amount of energy is certainly not going to have an observable effect on the long-term climate of the atmosphere, because the amount of energy in a wind or a storm, I mean, a big hurricane has as much energy in it as 100 nuclear bombs. So a wind turbine is not going to take much out of a big storm.
Sorry.
In terms of the, it will have a small effect, I guess, in terms of chaos, just like the flapping seagull wings, but it's not going to be a systematic effect that either changes the weather one way or another, and it's not like it would be more predictable without the wind turbine.
So it just means if we get a new wind turbine farm in the North Sea, maybe Brazil will get a rain shower in 2 weeks.
Yeah, maybe.
Okay. Okay, thank you. And so we have a question actually from our speaker for next week, Hugh Schunman, who asks, how likely is the Gulf Stream to go into reverse as used as a convenient plot device by so many disaster movies these days?
So I think that, so this is based on the idea that there's this Atlantic overturning circulation where water in the North Atlantic sinks down with the deep ocean, travels to the south over hundreds of years, and then comes up again in the southern hemisphere. It's a big cycle. And the idea is if the ice caps melt, then the water at the poles will be less salty, it'll be less dense, and this will ruin this overturning circulation, bend the Gulf Stream, and send us into an ice age. I don't believe that has ever truly been considered scientifically likely, despite how often it goes into disaster movies. But I could be wrong on that, but I don't think that's considered likely or even really possible, rather.
Okay. Yeah, as someone who works in the life sciences, there are often things in films that scientifically would never happen, but
yes,
are quite fun to have in films. So just time for a few more. We've got a question from Caroline Gregory, who asks, I noticed an increase in aeroplane vapor trails again this week compared to the clear skies of the lockdown. Do artificially produced vapor trails significantly affect the weather?
It's an interesting question. I don't think they do. I think that in theory, they could, but the width of obviously a vapor trail is very long and thin, and it doesn't actually take up that much area in the sky. And given that, I think it's like over half, it's like 60% of the atmosphere is cloudy at any given time. The small changes in the total amount of cloud caused by aeroplanes is not very substantial. I think we should be much more concerned about the CO2 they're pumping out while they're up there than about any effects from the vapor trails.
Yeah. Okay. Thank you very much. So just having a look. So I don't think we've got any more questions coming through. So thank you very much again for your talk, Josh. I found it really interesting. And we'll correct everyone from now on who mentions the butterfly effect, and we'll tell them that actually it's the seagull effect, and they need to thank the seagulls. Okay, so thank you very much. Just finally, a reminder about next month's talk. I'm going to bring Alphonse in, and he will be able to introduce to you a quick blurb introducing our talk for June. Alphonse.
Yes, so you have already seen one message from Hugh Schönmann. He will be talking about nuclear safety in next month's talk. And of course, in the early years when radioactivity was discovered, nobody knew if there was any danger related to it. Actually, quite the opposite. I think in the 20s or 30s, people were selling radon cream because it was supposed to be healthy for you. We, of course, now have learned the hard way that radioactivity can be dangerous if you don't treat it separately. And what those people in the early years have learned, and what we learned later about the potentially dangerous effect of radioactivity, that has now all been folded into international safety standards. And how this evolved over the decades, that's something that Hugh Schönmann will talk about in a month from now.
Okay, thank you very much, Alphonse. Thank you again for everyone who tuned in this evening. A reminder that the video will be saved on YouTube, so if you do want to go back and watch it, feel free, and let people know if they want to catch Josh's talk after this evening. Thank you, and we will see you in a month.